So from computer vision, we'll move next to NLP. And when we talk of NLP, I cannot think of any better name than Professor Pushpak Bhattacharya, who's from IIT Bombay, as probably most of you know, and now divides his time between IIT Bombay and IIT Patna, where he's the director for IIT Patna. Over to you, sir, Pushpak.
Okay, so yeah, from vision to language. My talk is on state of art for NLP, and I have also added some observations and insights based on whatever we have seen for a number of years. Okay, so I'll make a few remarks on the nature of NLP as such. Then I'll take a representative problem, talk about the new world order for NLP. Then some trends, Indian efforts, and draw some conclusions and future work. So natural language processing is one of the areas of AI, and the remarks that Professor Raj Reddy made in the morning sort of contextualizes remarks on AI computer vision also, and we can draw from those remarks. So the areas on the outer circle are the ones which are closer to human beings and real life applications, but all of them draw from very fundamental ideas and techniques of research, reasoning, learning, and some planning also. So we have always believed that natural language processing is a confluence of linguistics and computation. We believe linguistics is the eye and computation is the body. We can see on the top layer the basics of basic ingredients of linguistics: lexicon, morphology, syntax, semantics. And at the bottom layer, the nuts and bolts of computer science, probability theory, machine learning, graphs and trees, and so on. And this interaction between linguistics and computer science gives rise to very important areas whose utility as well as research interest are supreme, like sentiment analysis, summarization, morphology analysis, machine translation. All these are extremely big areas, and they have a tremendous application. Next, please. So just to make the point, that linguistics is the eye really, and computation is the body, I would like to make this example and put it in front of you right in the beginning. Okay, just to emphasize the point that this physics for computer science, linguistics for natural language processing, physics for computer vision, linguistics for natural language processing, physics, phonetics for speech, I think they will always remain. They can never be discounted. So here is an example. This is the distributional hypothesis from Harris back in 1970. Words with similar distributional properties have similar meanings, and Harris does mention that distributional approaches can model differences in meaning rather than the proper meaning itself. So this particular idea is the foundation for word embeddings or word vectors. So this is the linguistics is the eye point. Now let's see the computation is the body point. Next. So we have these CBOW and skipgram models for generating word vectors or word embeddings. So in skipgram, what happens is that a word is presented, its one hot representation is presented to a feed-forward network, and the output is prescribed as the contextual words for that particular word. For example, if dog is the input input word, one hot representation, then all the contextual words for dog, especially the content words like bark, policeman, vigilance, and so on, they are placed in the output layer in the form of a supervised learning situation. And CBOW is exactly the opposite. The context words are placed one hot representations, and the output is the word itself. Okay. So now the weight vector for the neuron in the one hot representation becomes the representation of the word. Okay. So the weight vector represents the word. Next slide. So now if we take an example here, when we hear the word dog, by association quite a few other words appear in our mind, and they also appear in the syntactic environment. So bark, police, thief, vigilance, faithful, friend, animal, milk, carnivore, and so on. Similarly, for the word cat, we have associated words from the corpora. Similarly for candle. Now the similarity between dog and cat is much more than the similarity between dog and lamp. as is shown in the associated word list also. Now, this is an intuition we have. This is also specified by Harris's distributional hypothesis. And next slide, please. And and if we present these words to the neural network, it is these very same words which appear by excitation at the outermost layer. Okay? So, the representation in this case means the similarity of the words through this representation in the weight vector form. So, this is the way we have captured the word embedding, and we take it as the meaning of the word. Okay? Next, please. So, coming back to this aphorism, linguistics is the eye and computation is the body. The encode decode deep learning network is nothing but an implementation of Harris's distributional hypothesis. Okay? So, this 1970 hypothesis has appeared as the word embedding trained through a feed-forward neural network by applying backpropagation algorithm. And this whole network is nothing but the implementation of that particular principle. Linguistics is the eye, computation is the body. Next, please. So, natural language processing, we know, is a layered task going from morphology at the bottom, which processes words, and transits through part of speech tagging, chunking, parsing, semantics, going up to tough problems like pragmatics and discourse. And natural language processing is also a multidimensional problem. There are words in the x-axis, y-axis are the problems with respect to language processing, and computer scientists are interested in the other axis, which is algorithm design. Now, the property and the personality of the language is very important. We have a very favorite example of ours, Ghara samurchyaane mala sangitle. So, this is a Marathi sentence, and the English sentence is, the one who is in front of the house told me. So, this is the way languages represent information. Ghara samurchyaane is a continuous string, and English has this isolating behavior. It has taken different morphemes from that long string and has different words representing the morphemes. So, this difference of property between the languages is important to keep in mind for algorithm design. Next. So, need for NLP is well known. We have to track the sentiment of people. E-commerce companies are very interested in this, and as Professor Reddy mentioned in the morning, translation is going to be a very, very important problem in the years to come. Next. Now, machine learning has become one of the important paradigms of natural language processing. And in machine learning, what we do is that we look at instances and arrive at an abstract concept by which we can classify the objects. So, when instances of tables are given, what we arrive at is the concept of tableness in some approximate form, and that is refined gradually in presence of more data. Okay, so, what we are acquiring is the concept of tableness, not particular tables. Next. So, this picture I am very fond of. Natural language processing and machine learning have got married for the benefit of both fields. Next, please. Now, natural language processing, the challenge of natural language processing comes from the fact that there is ambiguity at every stage, and this is what makes machine learning and natural language processing come close to each other. Ambiguity processing means choosing one amongst many options. So, that precisely is the classification task. We choose one of the many classes present. So, there is ambiguity at lexical level, ambiguity of words. The word present can mean time or gift. There is structural ambiguity, 1 and 2 bedroom flats live in ready. Live in ready has to be grouped together. Similarly, 1 and 2 bedrooms have to be grouped together, not only as such, but also recursively. They have their internal structure. This is a very famous sentence in semantics, flying planes can be dangerous. What is dangerous? Flying or the planes. Pragmatic ambiguity, sarcasm is a case of pragmatic ambiguity. If I am not given any attention in a party, and while I am taking leave of the host, if you ask me how did you like the party, then I reply, or let us say retort, I love being ignored, okay, which is a sarcastic sentence. So, the surface meaning is different from the intended meaning. Forward. The other challenge of NLP is multilinguality, and if you had seen the list of things that Professor Reddy put up, multilingual computation is listed as one of the basic needs of our civilization. Next. So now an important point about the nature of NLP and its interaction with machine learning. Rules have been used in artificial intelligence always, right from the beginning of AI. Okay? Even when data-driven computation is used, underlying mechanism is rules, even though they are not apparent, and we would like to extract those rules from the machine that has been trained. That is called the research on explainability. Rules are very good for explaining the computation. And we also would like to believe that we should not learn when we know the underlying knowledge. Only when the phenomenon seems arbitrary at the current state of knowledge, then we would like to go to data. For example, Bahut Dhanyabad is translated as many thanks, not as several thanks, and there is no explanation for this. Okay? So since this is a fixed behavior, we would like to extract this pattern from the data and use it. Next, please. So in this scenario, probability has played a very, very important role. This is a favorite example of mine again. If we look at these 4 sentences, the sun rises in the east, the sun rises in the east, the SBN rises in the east, and the sun rises in the west. All the sentences have some defect or other, grammatical mistake, spelling mistake, semantic mistake. The first sentence is correct. And when we compute the probability of these sentences, for the first sentence, the probability comes out to be highest. What is the meaning of the probability of the sentence? Next slide, please. The probability of a sentence means the probability of n-grams and their product. So probability of sun rises in the east is P probability of sun into probability of rises given sun, probability of in given sun and rises, probability of the sun rises in, and so on. So this is the quadrigram probability. So when we try to compute this probability, because of the fact that rises in the west as a quadrigram is less frequent than rises in the east, as it appears in the corpora, the probability of the first sentence comes out to be the highest. Can you go back once? Yeah. So the probability of the first sentence comes out to be the highest, and it produces an illusion that the system understands grammatical mistakes, semantic mistake, and spelling mistake. Okay, so this very simple calculation, which is robust and fast and based on simple ratio of counts, creates an illusion that the system is aware of grammatical mistake, spelling mistake, and syntactic mistake. So this method of doing AI, okay, according to me, is a slightly different world order, and this is going to stay for quite some time, okay, because data is available. Next. Next, please. So this particular power of data and simple processing of data was brought out in 2014 by a paper from Google, which also got a lot of press, and Jawahar mentioned this in plentiful number. There are lots of papers on automatic image captioning, and the main methodology is simple. We do image processing on the image and natural language processing on the caption, and put features and parts in correspondence. Next slide, please. So one more slide. Yeah. So you see all these images have been captioned automatically, and now there are slight mistakes which are also curious. So look at this second image. 2 dogs play in the grass. Actually 3 dogs are playing, and also the last but one image, red motorcycle. Actually the motorcycle is pink. Now one begins to wonder why a system which has done everything right, why does it make these mistakes of counting the dogs here and the color of scooter there. So this we know from the history of AI is the sign of shallow understanding. Okay, systems which have shallow understanding can make curious mistakes which are otherwise all right, but make some mistakes which are unexplainable. So next, please. So this kind of shallow understanding is the characteristic of NLP, ML, AI, and maybe vision speech also, where we can sort of write an equation with some violation of notation. Deep understanding is equal to shallow understanding plus big data. That seems to be the world order today in terms of research. Next. So this reminds us of the grind methodology. show umpteen number of problems for a particular concept. For example, Newton's third law of motion. Here is the problem of spring, there is the problem of recoil by a gun. All these are explained by Newton's third law of motion. But what happens today is the students are subjected to a very large number of problems being solved. And next slide. And what they do typically is memorize the patterns. There are multiple choice questions. Match the pattern, eliminate choices, select from a few. And it seems they do not have a unifying theme which runs across the problems. Okay. So next. So there is an uncanny resemblance to today's NLP as I see it, you know. There is this kind of huge memorization of pattern along with probability distribution. So if I take this example, I love being ignored. This is sarcastic yes, non-sarcastic no. This is the hard max decision. The movie is great for putting you to sleep, slightly difficult because the sarcasm is not overt. So this is sarcastic with probability 0.9 and non-sarcastic with probability 0.1. So instead of classifying in a hard manner, what we are learning is a probability distribution where all the classes are probable with different probability values. Okay? And this corresponds to actually extracting patterns and giving them probabilities, assuming some kind of probability distribution on the underlying data. Next. So the main methodology in NLP, also I think in many other fields of AI, is this. Object A and object B are put in correspondence, and parts and features are extracted from both the objects, and we establish correspondence between these parts and features. We go from larger correspondence to smaller correspondence, and the methodology is most of the time expectation maximization. And we learn these mappings, we use these mappings in a new situation called decoding. This is the main methodology which is applied across machine learning driven NLP. Next. And linguistics and computation interaction happens through annotation. Annotated data is better than raw data. That dramatically changes the way computation is done. But good annotation design and good annotators are very difficult to find because they have to understand both statistical phenomena and linguistic phenomena. Next. So I take a representative problem now, and this is the problem of numerical sarcasm. It shows, you know, why rules, classical machine learning and deep learning, all of them are important. Why it is necessary to perspectivize all of them. Next, next please. So about 17% of sarcastic tweets have origin in number. This phone has an awesome battery backup of 38 hours. This is non-sarcastic statement, positive sentiment. Last sentence, this phone has a terrible battery backup of 2 hours, non-sarcastic, negative sentiment. The second sentence is curious. This phone has an awesome battery backup of 2 hours. Why do we resort to sarcasm? Okay, why can't we plainly, directly say, express our negative sentiment? So this is an interesting question, why people use sarcasm. I think human beings inherently like dramatization. They also like forceful articulation. And here, one of the hypotheses is that sarcasm has this effect of lowering the defense and then attacking. Okay, and there, at that time the attack is much more forceful. So this phone has awesome battery backup, fine, the defense is lowered. Okay, and then you dramatically come back saying backup of 2 hours, which is a negative sentiment. Okay, so there are many theories about why sarcasm is used as an instrument for communication. Next. So numerical sarcasm, all these are examples of numerical sarcasm. Waiting 45 minutes for subway in the freezing cold is so much fun. So much fun is positive, but waiting 45 minutes in the subway in freezing cold is negative. So simultaneous presence of positive and negative sentiment indicates sarcasm. Next. So there are important data sets in the area for sarcasm task. Next. So what is done in sarcasm research is numerical sarcasm detection is this phone has an awesome battery backup of 2 hours. It is passed through natural language processing. This is dependency parsing output. Next. So we create tuples of this kind, phone, awesome, battery backup, etc. noun phrases. The number is 2, unit is hours. And the algorithm goes as follows. Next. In rule-based matching, system, I love writing this paper at 9 a.m. This is a new sentence. The matched sarcastic tweet is, I loved writing this paper daily at 3 a.m. That is sarcastic. Now, since 9 is not close to 3, the test sentence is non-sarcastic. I'm sure you are raising your eyebrows, okay, because this is so ad hoc. See the next example also. Test tweet, I am so productive when my room is 81 degrees. Matched non-sarcastic tweet is, I am very much productive in my room as it is 21 degrees. The absolute difference between 81 and 21 is high, and therefore the test tweet is sarcastic. So this is the rule-based system. Okay. Now the rule-based system is naive, very ad hoc. Agreed. Next. So then if we go to machine learning, when decision seems ad hoc, we would like to go to data and make these decisions come from the data itself. So here classical machine learning, and we use different features like positive word, negative word, and so on. Next please. Positive emoticon, negative emoticon. Next. Punctuation features. Next. And then, since features also depend on human beings' whims and fancies, okay, we would like to eliminate even that part of computation and make it completely deep learning based, very little feature engineering. So next please. So convolutional neural network, feed-forward network with backpropagation. Next. And here are the results. So we find that deep learning based approaches give about 93% accuracy. Machine learning based approaches 80%, rule based system 82%. Okay, both of them are 80%. What is the main difference? The difference is that rule-based system, the decision is ad hoc. Coming from human beings, it is ad hoc. The problem with machine learning-based system is that features are being used. Features are also given by human beings. The ideal deep learning system will eliminate all human intervention, and everything will come from data. That is the ideal deep learning scenario. And the message being okay. The next insight is that ad hocism in the decision. We rely on the data to give us the decision threshold then. Okay? Then you can remove this ad hocism by relying on data. If we go to machine learning, then human intervention is little reduced. Still the features are coming from human beings, and even that level of human intervention is removed when we resort to deep learning system. Next. Message is that rule-based systems are great for intuition building and explainability. That we cannot take away from rule-based systems. Okay? The idea for building the machine comes from rule-based systems. However, some human decisions seem to be ad hoc, so relegate that decision to come from data. And finally, in the final step, resort to deep learning to have even feature engineering coming from data. So this is the trend. Okay, this is the trend: rule-based system, classical-based machine learning-based system, and then deep learning-based system. Next. So the new world order for NLP/ML is the following. There is this trinity of data, technique, and idea. In this new world order, data has become available. Techniques have improved a lot. Okay, a lot of insights from machine learning. Now there is this playing field where people with ideas can make use of data and technique to come up with very useful systems. Okay, but this playing field is not a level one. There are haves and have-nots, and data application and more data is a steeply ascending gradient. Google's, Facebook's, Uber's have tremendous amount of data. So they will always try to either outsmart new entities with ideas or will try to acquire them. Next. So I saw this San Francisco based startup called Postmates, which aims at getting anything delivered in minutes. Okay, the idea is very similar to Uber. Like Uber has a fleet of cars with drivers, Postmates has a fleet of couriers, currently about 13,000 who can deliver goods locally. So huge amount of data is gathered and subjected to analytics to reduce delivery time by drafting nearest courier personnel to pick items from specified shops and deliver, just like Uber drafts its drivers. Okay, so same idea. Next. So Apple is very interested in bringing in multilinguality, sentiment, etc. in its Siri system, where again NLP plays an important role. Next. NVIDIA is more interested in attacking very fundamental question. Lot of deep learning is actually based on matrix multiplication. So they would like to make matrix multiplication faster and faster. Next. Now a common startup theme seems to be prediction of problematic instances out of conceptual space. So predicting if a loanee will turn out as defaulter, an organization will fall into financial distress, a rentee will prove bad for Airbnb. So those are all one class of problems, okay, which startups are handling. Next. But another common theme is we have services like cars, shops, restaurants, movies, etc., and people wanting service like travelers, consumers, moviegoers. And between these two, there is this matchmaking software. Uber, Lyft, Make My Trip, Postmates are nothing but matchmaking softwares. Okay, next. And therefore, the methodology is the services register themselves with the software. People wanting service, they download the app, and that builds the bridge. And then matchmaking takes place for first service, quality of service, and customer satisfaction. Collect users' feedback in spoken and written form. This is a very, very important trend for all these matchmaking softwares. Next. Indian effort, this has been mainly multilinguality driven, and many of our very well-known researchers are right in this team, right in this room. In 90s, we saw 5th generation computer project, IISc architecture, IITM expert systems. The then NCST doing NLP, ISI computer vision, TIA for speech. Machine translation has been a large effort since 1980s. Many institutes have been involved. Cross-lingual information retrieval, we have been leading this effort from IIT Bombay. Next. Indian language lexical resources like Indian WordNets. Information extraction, very strong groups exist in KGP, IIT Delhi, IISc, IIT Bombay, IIT Hyderabad, IIT Patna also. Speech and NLP, IITM, TIA for IIT Bombay, OCR and NLP, IITD, IISc. So these institutes have been contributing a lot to Indian language, NLP and speech. Next. So future outlook is as follows. It is a reality for NLP that lab ideas are going to the land. Okay, they are becoming large utilities, very, very, very useful utilities, making a lot of money. And the processing is based on quick and robust computation. Quick and robust computation. Shallow understanding, shallow processing, but a lot of data. This is here to stay. And NLP and speech marriage is inevitable, led by speech, NLP as the back end. Okay, so speech, voice activated systems are going to be there, but they will be helped a lot by natural language processing at the back end. Chatbots are becoming very ubiquitous. Banks, insurance companies, airlines, all of them want chatbots. Emotion and opinion tracking, we'll have to ignore this only at our peril, and there is huge possibility of economic impact. I'll end with some philosophical questions. One, next. Method changes, but the philosophy does not. Okay, method changes, but the philosophy, fundamental philosophy doesn't. Classical, statistical, and deep learning. Method changes, not the fundamental principle. What is the fundamental principle? Let's remember this. NLP and machine learning works on the principle of establishing correspondences. Okay, there are large objects which are put in correspondence. Their parts and features are put in correspondence by expectation maximization or some such algorithm. This is the basic methodology. And then we apply these learned mappings to new situations, which is called decoding. So this particular thing hasn't changed, whether it is rule based or machine learning based or deep learning based. This fundamental principle hasn't changed, will not change according to me. So this is based on the correspondence of parts and correspondence of features. Now, when we learn this correspondence of parts and features, the ingenuity lies in modeling the probability. Okay, what exactly is the probability distribution? That is the crux of the matter. That's where human ingenuity will play its role. Next. And the philosophical view of neural network versus language is the following. In deep learning or neural network based computation, we know there are only two kinds of representations, vectors and matrices. In fact, only one, matrices. And operators are only two, vector addition and vector multiplication. If we go to the world of languages, the representation is much, much richer. There are characters, words, sentences, paragraphs, punctuation, syntax tree, meaning graph, silence, modulation, etc., etc. And operators, concatenation, reversal, reorder, implicature, irony, metaphor, sarcasm, all are operations of language. So a very, very important question is this representation and this matrix, only one, only two, can this capture this whole rich gamut of operations and representations in the field of language. Okay, next please. Thank you.
Thank you, Professor. We'll take probably one question since we are running a bit over time. One question in the audience. Anyone? Yeah. Just wait for mic.
Like in word to vector representation, let's say one word is there the river bank of Ganga something, and the State Bank of India increase the interest rate something. So these two words are placing different context, but the represent, how will you make a word to vector representation for these two?
Yeah. So this is an example of word ambiguity, bank as a river bank or bank as financial bank. So if you create the word representation from the corpus as such, okay, then you will not have two different representations for two different senses. Okay. However, if you generate word vectors from domains, then the representations will be different. The other thing is this explainable word vectors, and Parth has proposed this, worked on interpretable word embeddings. Kevin is working on this. So you can trace components of the word vector which correspond to those domain specific attributes. For example, the financial bank has very close association with money, for example. Okay. So that particular component maybe we can trace to a particular position in the word vector.
With that, we'll close this talk. Thank you very much, Professor.